The following lecture is recorded and produced by Momin Ahmed Rizvi, and the accompanying note for this lecture can be found on AurParho.live, and it is called Polar Coordinates, Further Pure Maths 1. So if you have that downloaded, open it up now, or if you don't have it downloaded, go ahead and download it and open it up now because it'll be useful to follow along with that note during this lecture.
The way to do this is, first of all, you find the y component. You find the y component by multiplying r by sine theta. So r is a plus 1 plus a times 1 plus sine theta. You multiply this by sine theta to get y. So y is actually sine theta multiplied by a times 1 plus sine theta. Let's multiply. We would get a times sine theta plus a times sine squared theta, right? Now let's find the derivative. The derivative of sine is negative cos, so negative a cos, not negative a, just a cos theta, and the derivative of sine squared would be 2a cos theta sine theta, right? And let's set this equal to 0. And let's take a cos theta common, so we get 1 plus 2 sine theta equals 0. When this whole thing is 0, when either of those are 0, so when is cos theta equals 0 and when is 1 plus 2 sine theta equals 0. Cos theta is 0 at pi over 2 and 3 pi over 2. 1 plus 2 sine theta would be, when is sine theta equals negative half? Sine theta is negative half at 7 pi over 6 and 11 pi over 6, right? So let's look, these are your values of theta at which the tangent is parallel to the initial line, at which there is no change in y as x changes, right? So the values are pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6. And let's look at the graph and see why it makes sense. Okay, so this blue line that I told you that you can probably guess, this is your pi over 2, right? This line that is already drawn, so let me take this color. This is the line, this is the tangent when it is at 3 pi over 2, this blue one that I'm drawing, right? You can also see, you can see this is also this, its gradient is also 0, and then the 7 pi over 6 is somewhere over here and 11 pi over 6 is somewhere over there, so these are your values at which it's tangent, right? So this is your dy d theta, and a very similar case is of dx d theta, which you can also probably tell from now. Let's say you have the same graph. This is very poorly drawn, but okay, let me try to draw it a bit more accurately. 1, 1, 1, 1. Okay, it starts. These are your points, right? And it looks something like this. It's still poorly drawn, but let's just accept that. Okay, what if I ask you at what values of theta is the tangent perpendicular to the initial line, right? So whenever a graph is perpendicular to the initial line, we know its gradient is undefined because y is changing infinitely as x changes. Basically, there is no change in x, right? X is constantly at this value. So since the change in x is 0, anything divided by 0 is undefined, right? So we want to find the value at which dx d theta is equal to 0, right? And you can also see this, why we're wanting this value. At this value of theta, r is this, and the x component is this. At this value of theta, r is this, and the vertical component is this, until it reaches some value over here where r is this, right? And until it reaches this, oops, until it reaches this value, right? So as you were increasing over here, as you were increasing theta, the x value was also increasing. It went here, it went here, and it went here. And then after this, if you increase theta, it will be some value less than this. So this is your peak value. right? And at this, the tangent would be something that is perpendicular to the initial line, right? So let's find out what dx d theta is. And what is x? Let's make a line over here. What is x? X is basically the r multiplied by cos theta, right? So r is actually a1 plus sine a1 plus sine theta, multiply that by cos theta, you get cos theta plus a cos theta sine theta. Okay, let's take dx d theta, so the derivative. Derivative of cos theta is negative sine theta, and then let's apply chain rule. A cos squared theta minus a sine squared theta. Is this correct? Yeah, it's correct. Okay, so actually let's get rid of the a's first because we set this equal to 0. Let's take a common. So sine theta plus cos squared theta minus sine squared theta minus sine, yeah, missed a minus sign there, equals 0. So let's convert all of these into sine forms. So 1 minus sine squared theta and sine square, right? So this becomes minus 2 sine squared theta minus sine theta plus 1 equals 0, right? And I like to keep my highest powers positive. Okay, we can middle term break sines 2 sine squared theta plus 2 sine theta minus sine theta minus 1. Let's take 2 sine theta common. Sine theta plus 1 minus 1 sine theta plus 1 equals 0. So you get the factors as 2 sine theta minus 1 sine theta plus 1 equals 0. Excuse me. And let's equate these to 0. Sine theta is either half or sine theta is negative 1. Sine theta is half at which is a half at pi over 6 and 5 pi over 6. Sine theta is negative 1 at 3 pi over 2, right? Is it at 3 pi over 2? Yeah, it is at 3 pi over 2. Okay. And let's look back at the graph and see why this makes sense, right? So at 3 pi at pi over 6, the tangent is perpendicular, and then at 5 pi over 6 it is again perpendicular, and then the next value that we got was 3 pi over 2. So basically when you look at this cusp, like, let me redraw this, what the graph looks like. It looks something like this. I'm drawing it bigger on purpose so that we can see it easily. Right. So this portion of the graph, right? When you look at this, the graph is coming closer and closer the the y-axis, to the line pi over 2 or the line 3 pi over 2, right? And eventually when you're at 3 pi over 2, they become a common tangent, that is 3 pi over 2, and this is of course perpendicular to the initial line. So these are your values of theta, right? And the next part, so we're done with derivatives, right? So the next part is actually integration. Integration. And this is really where, in my opinion, it gets a bit annoying in terms of the algebra, but it's all fine. It's not too much of a hassle, right? So let's take any graph, right? Let's say something like this, right? So you've been given that r equals to something, something, right? And you want to, let's say this is pi over 2, let's say this is pi over 2, and you want to find, and let's say this is pi over 3, and you want to find this area, right? So the first thing you need to remember is that when you're integrating the graphs, when they're in polar form, you don't just integrate them directly. You don't do integral of r. What you actually do is half integral of r squared d theta. And let me show you why this makes sense. So if I take this specific graph, if I take this specific graph, and if I start chopping these into, if I start, let's say, This is some change in theta, right? And if I start chopping these into finer and finer portions, right? If I chop a curve into very, very, very fine sections, what I eventually get is some sort of a sector, or even what you could call a triangle, right? You would agree, because any curve, if I take very, 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 very small values, it would be some sort of a sector or a triangle, right? And what's the area of a sector? You might remember it's half r squared theta, right? What's the area of a triangle? It's half r squared sine theta, right? It's half AB sine theta, and AB are for very, very small values. The radius is pretty much unchanged, right? And for very small values, theta is approximately equals to sine theta. So these two values are the same. So this is the reason why when you're integrating, this is actually the formula for the area, right? So if this was something, if I had to integrate this, what I would do is I would take the integral from pi over 3 to pi over 2. And what integral of pi over 3 to pi over 2 basically means is that I chop all these into smaller and smaller sections till pi over 3, right? And I do the same till pi over 2. And first I sum up the area of all these small sectors till pi over 3. And then I do the same for the sectors till pi over 2. And then I subtract the red portion from the purple portion to eventually get our desired area, right? So let's look at example. It might be easier. The example that are in the notes is of 1 plus cos theta. Okay, so let's take this is a question. Let's You've been given a times 1 plus cos theta, and you need to find the area that is between pi over 2 and 3 pi over 2. And for derivatives, or generally for any polar coordinate question, it's very helpful to have a general sketch in mind. And this is why sketching might be pretty important. So 1 plus cos theta looks something like this. It looks something like this. You could think of it as a rotated sine curve, because sine 90 minus theta is cos theta basically. But that aside, let's integrate this. So it would be half all of this squared, a squared 1 plus cos theta squared, and we're summing to d theta, right? So let's take the a squared out. A squared integral of 1 plus 2 1 plus 2 cos theta plus cos squared theta with respect to with the change in d theta, right? This would be equal to a squared over 2 1 plus 2 sine theta. Actually, let's change it first. This would become 1 plus 2 cos theta, and using identities, we know that cos squared theta is actually cos 2 theta plus 1 over 2, right? So this would become 3 over 2 theta plus 2 sine theta plus sine 2 theta over 4, and we're doing this till from pi over, what were the values? From pi over 2 to 3 pi over 2, right? So from pi over 2 to 3 pi over 2. Okay, so let's plug in the values. You first plug in these values, and then you plug in minus of these values, right? So let's plug in 3 pi over 2. So 3 over 2 times 3 pi over 2 is 9 pi over 4 plus 2 sine 3 over 2, 3 pi over 2, right? And then sine of 3 pi would be 0, so let's add a minus there. Minus 3 pi over 4 minus 2 sine pi over 2, and then again this becomes, because it's multiplying by 2, it becomes pi, so it's 0. Let's do the arithmetic. 9 pi over 4 minus 6 pi over 4 would be 3 pi over 2, right? Sine pi over 2, sine of 3 pi over 2 is 1. Sine, is this correct? Sine of 3 pi over 2, sine of 3 pi over 2 is negative 2, and sine of pi over 2 is negative 1, and sine of pi over 2 is 1. So it's become negative 2, negative 2, right? And if I just take the divide by 2 over there, it would be 3 over 4, negative 2. Let me check if this is correct because I think it should be plus 2. Oh, my bad, my bad. This was in the notes, this was actually minus, right? But if you do it as plus, this would be the actual answer. Right. The last part the last thing that's there is to it is the integration by parts. Integration by parts. And this is just a method of integrating, and it's used sometimes when you're integrating for polar coordinates. So when you study the product rule, the derivative of two products, let's say uv, would be uv prime plus vu prime, where prime basically means derivative, or you might remember it as left times derivative of right, right plus right times derivative of left, right? So we kind of use this to sometimes we use this in integration sometimes when we have two products. So for example, if we know that these two are equal, right? This is equal to this. So if we take integral of this equation, integral of the derivative of this thing is equal to integral of uv prime plus vu prime plus the integral of u prime. Well, the integral of a derivative is just the thing itself because you're taking area of the slope. So this would be uv. This is equal to the integral of uv prime plus the integral of vu prime. And then let's make integral of uv prime the subject. My u's and v's are very similar. This would turn out to be uv minus the integral of vu prime, right? And this is what integration by parts is. Whenever you want to find the when you want to find the integral of two products, you might want to try and use this called integration by parts. So let me give you an example. Let's say you have r equals theta times cos theta, and you want to find the integral of this. Let's say r square is equal to theta times cos theta to make my life easier. So let's say you want to find the integral of this. So it would be half times whatever this thing is d theta, right? So what is the integral of theta times cos theta? Let's use this thing. Integral of theta times cos theta would actually be, first of all, let me tell you something about the acronym LATE, right? So LATE basically stands for logarithms, logs, algebra, trigonometry, and exponentials. Exponent. Oh my God. Exponentials, right? And this is basically the decreasing order of preference for the taking of u, right? So for example, if you have any log in the function that is most preferred to be taken as u, here we have algebra and we have trigonometry. So a comes before t, so I will take u, the theta as u and cos as v. So this is actually v prime. So when I need uv, so it would be the theta times integral of cos theta, which is minus sine, right? And which is just sine, not minus sine. And then minus the integral of sine theta times the derivative of theta, which is just 1, right? And this would be theta sine theta minus cos theta. This would be theta sine theta plus cos theta, and this is your answer to this, right? So just 1 over half theta sine theta plus cos theta plus c would be your answer, right? And this is it. This is all there is to it. Integration, you might want to practice so that you get used to the algebra and stuff, but this is it.